There's more value in the connections outside of these talks than actually listening to the talks themselves. Like we've spoken to a lot of very experienced, very tenured people who have lots of, great stories and mistakes that we can learn from so that we don't have to make them as well.
Hello everyone, I'm Katherine Rocha, and we're going to be looking at POSIX networking and the different operating systems and how that implementation works in different operating systems. So here's just a little bit about me. I'm a software engineer at Catalyst Space, and we have a custom flight software solution called Ether that's mostly in C++, but also contains some Python. And just so that way you're aware, some of my hobbies include things like genealogy, and that's actually something that I take back and pull into most of my talks, because I think the idea of understanding the past to make better decisions in the future, as well as understanding what our impact is for the future, are some of the most important things that we can do. So here's just a little bit about the company that I work for, just so that way everybody understands kind of why the things that I'm looking at are the things that I'm looking at. So Catalyst, we're trying to make satellites that allow us to do dynamic space operations. So your spacecraft can continuously be upgraded. We can end up doing, moving it into a different orbit, allowing us to extend lifespan of spacecraft that are already up in space today. So we kind of have three different areas that we tend to work on, and I tend to focus more on the upgrades and platforms and the life extension. So here's the largest spacecraft that we work on. And it's pretty big, but we also work on a smaller one that's kind of more for like the proof of concept, along with doing some other stuff as well. And those are the two I work on, and we run Ether on there. And with that comes with a lot of capabilities. We're more memory rich than your typical space application, and we're actually able to run Debian in space. So this is amazing and awesome, but that means that we don't have all the issues that you typically have in space operations. So now comes site. So one of my coworkers actually started working on this project, and hardware had already been determined, operating system had already been determined, and we were talking about it, and he actually was forced to use a different operating system that wouldn't allow our current flight software to run on that operating system. So what we needed to figure out was what's possible and what's not, and what can we pull across. Because with flight software, what really matters is having that software that's already been tested up in space, that we have verification that it works, verification that things act as expected. So we're gonna kind of look at a couple of different things here. So this is my investigation. There are a lot of things that didn't go right. There are some things that did, and we're kind of figuring it out as we go. And to quote Ben Dean, we're learning through play. So we're gonna kind of play around with using different operating systems before we have to figure out what networking works, what doesn't, what can we do differently for the future in order to design our libraries and design our user code, so that way we don't have these problems when the situation comes up and suddenly we're having to use a real-time operating system that we didn't expect to, and suddenly none of what we have works for that situation. And feel free to ask any questions as we go along, so that way we're all on the same page. Cool. So why do we need library support? So we have these long-term space projects, and we end up having to have our software work for a really long period of time. And so being able to use different libraries and use code that's modern is really helpful. We're actually currently running C++ 23. And so it's really helpful to be able to use the modern stuff in these systems where it's like we need to have this longevity for a long period of time. We also have really early tooling freezes. So before we get into testing, we're gonna freeze early. And we want to have compatibility across our whole entire company tool suite, as well as the industry likes to try and share some things across different groups. So being able to have that sharing is really important. And we want our mission critical edge code to have the same support that some of our desktop code has currently. So we're going to look at like open systems. So open systems have a bunch of different goals. The first one's interoperability. So that's the ability for us to move data and information across networks. And then application portability, so that's moving application programs from system to system. And then user portability, which is, so if you're a user and you're gonna access a different system, can we actually be able to interact with the system? A good example of this is if you use mostly Linux and decide to hop onto Windows and do something in PowerShell, and start moving around, you're gonna start hitting walls really quickly because it's not easy to use when you aren't used to it. So now we're gonna look at POSIX. Now, the key word with POSIX is portable. The idea that we're gonna be able to use POSIX on a variety of different systems, on a variety of different things. And these purposes are actually from one of the POSIX websites. The idea being we want POSIX to be able to be the thing that we can use and have that source of truth. So that way when we're writing different code, we can use this and know this is going to interrupt and be able to work with someone else. So it's all going back to that open system concept of this is going to work because we've used it in another thing as well. Cool. So for a typical POSIX example, I like to think of like your operating system class. So in operating systems, I tended to have P threads. And when I looked at P threads, I was like, what does this P stand for? And it's POSIX. And I was like, well, when I use sockets, they don't have a P in front of it. So like, they must not be POSIX. So POSIX there stands for the POSIX Thread API. And what's interesting is when POSIX was being created, they were trying to figure out what standards already existed and what standards didn't. And so POSIX threads are something that were implemented before there was a standard that people were starting to adapt and all do. So they were able to kind of set the standard and use that. Versus when we look at sockets, they first appeared in BSD and are also known as Berkeley sockets. And so they took that already interface and were able to apply it to POSIX. That way you didn't have to rewrite all your code in order to be standards compliant. And it also follows the Unix's everything is a file model. So we're gonna look at a simple C-style networking example because when you're messing with things like sockets, you tend to start with C, unfortunately. But with that, we aren't really looking at how it works. We're more looking at how the API works because we want to be able to use that API across operating systems and be able to transport our code from one thing to the other and hope that the underlying stuff does the same thing. So this is a really simple example. And basically what it does is it pulls your NIST time server to get the current time. That's all it's trying to do here. And so when we look at this and we go at C, we're going to C++ify it. And so what the big things I think of is we're going to remove the struct keyword in front. We're going to remove the C-style cast, which thanks Ben and Jason for talking about the different replacement types for that. But you're going to use a bit cast or a mem copy. And then you're also going to migrate all your arrays to std arrays. Cool. So some of the calls that I think are really important to look for are socket, connect, read, and close. So socket's creating the unconnected socket according to the domain type and protocol, which make sure to take a look at those because those are important later in the talk when it comes to what some of the other operating systems do. Connect is going to connect the socket to a specific IP and port, and read is going to read from the buffer and then get data in. And then close is going to close the socket. And we aren't really focused, as I said, on the exact functions because there's a ton of documentation online, ton of examples online. If you want to figure out how to do sockets, go online and you're probably going to get a lot better of an example than something I'm going to give you. But we just want to see how the API is. And then we also have the #include sys socket, which is really important because we want that API and that file to stay the same. So first we're going to look at the POSIX standard, which you can access online. And when we just kind of take a far back look at it, we're like, okay, great. This reminds us of something, right? And it's man pages. They look almost exactly the same. And that's actually really cool because that means we are actually trying to use the standard in the man pages that are being accessed. And so what really should we do with this information? It's the idea of using multiple resources. So we should design to the page that enables the largest portability, but use the system man page as the source of truth. So use the POSIX man page to design our code. But if there's anything weird or anything out of the sorts, use our other man page for our specific operating system to ensure that we're getting the same behavior. And this issue isn't just present in real-time operating systems, but also when switching Unix distributions or moving from for example, from Ubuntu to FreeBSD, you can have some weird things where things don't behave exactly how you would expect them to. So now portability. We really want our code to work in as many places as possible. And traditionally that means running on multiple compilers and multiple operating systems. But one of the biggest issues for some of the embedded stuff is these different operating systems, like real-time operating systems, aren't ran in a lot of the tests and stuff, besides when you're working in industry and that's a requirement that you're going to use. And so we want to make sure that when we're doing stuff, we do our testing in the pipeline so that way we don't lose support. So adding stuff like running RTEMS with our networking to ensure that we're going to keep it, even if we aren't using RTEMS today, just to ensure that we aren't going to lose that support in the future. So let's talk a little bit about why we use real-time operating systems. So who here like uses real-time operating systems or has used them? Okay, most everyone here, so we'll keep it kind of brief. So the idea is we're gonna look at control. We wanna have our timing and deadlines. We wanna make sure that things are reproducible and that we can put it on the chip that we need to put it on. And it kind of splits the middle in between our main plus ISR and our operating system. So here's some examples. As you all probably already know, things like VxWorks, FreeRTOS, RTEMS, Zephyr, and then we have the Linux plus real-time. And there's the opportunity to do more on real-time operating systems without some of the overhead that Linux provides. So where an RTOS doesn't tend to align with other operating systems is in the initialization side. So it tends to be really customizable, but it only tends to be use what you need. And networking doesn't tend to be on by default. And this is really good because it allows you to reduce code size, increase determinism, and reduce power usage. But you also don't have all the tools and stuff that's nice to use like you do with with traditional Linux. So let's look a little bit at FreeRTOS, the first operating system, real-time operating system I looked at. So it's been open source for 20 years. Who here has used FreeRTOS? Cool, that's most of the room. And I actually didn't realize this. It's now part of the AWS organization, and they're using it for IoT devices. And then it's also pretty widespread. It's used in a lot of different places, and it includes just the real-time kernel. So it doesn't have some of the networking features. It only has scheduling functionality, inter-task communication, timing, and synchronization primitives initially, but you can add things like command console interface and network stacks after the fact. So for networking features, online they say they have the Berkeley Sockets API. And we're like, yes, this is gonna work. Our code's gonna move. We're just gonna copy paste, and this is gonna be so easy, and no one's gonna have to deal with this. And it's also fully reentrant in thread safe API. So we're like, great, we're checking all the boxes of good things here. And then I'm gonna let everyone take a look at this. Here's the API. Now, what's weird or problematic here?
All of it.
What?
All of it?
Yeah. So they decided to put FreeRTOS in front of everything. So now we can't just do our include copy paste and things are gonna work. So that's really unfortunate. Our include is different. We're just starting to run into a lot of little issues where things are not going to be portable. And then there's another weird thing here. And it's in that domain type protocol that I told you to look at earlier. So the last one, the protocol, it actually, in their instructions, so on POSIX, you can set it as 0 and it'll find the default. Here, the requirement in the standard is it has to be FreeRTOS iProto TCP to create a TCP socket or UDP to create a UDP socket. No other values are valid. So suddenly we're also diverging even more from something that we thought was standard. So we can't just do our Control F, put FreeRTOS in front of it, and it's all gonna work. So portability, it's really easy to use. It's easy to recognize, and it's similar to what we used before. So if anyone who's used sockets has used sockets before, you could probably put them in front of it, and they'll create a socket code, it'll work. You can take your existing things side by side and move everything over. But our code can't just be copy pasted, and we're suddenly losing all of that flight heritage that we already had because there still is a non-zero chance that we're gonna have a bug sneak in. So we're losing the ability to have the trust that we had before. And we can't just have our one library with library code and use it literally everywhere we want to use it. Sorry. It also has really good examples, and it can be really helpful for getting started quickly. So now what if we really want to use it? We're locked on this FreeRTOS infrastructure. We're going to keep using it. Then let's be kind of like Boost.Asio. We're going to add an API option, do a pound define, use the preprocessor, and do something to enable us to use it if it's this way, and then use our Linux style if it's the other way, and then just probably throw some error checking in to ensure that some of these weird divergence get caught on the back end. So that way our users don't have to mess with it and figure out how to use it. And this tends to be a really big thing that you end up using, is trying to isolate those differences and pull it out into your library code so the user doesn't have to mess with it. Cool. Next up is RTEMS. Who here has used RTEMS? Okay, we got one. So I actually learned about this at Flight Software Workshop this year, and they talked about RTEMS, and they were like, this is amazing, like you should take a look at it and try and use it. And that's part of one of the other drivers for this talk, was getting the opportunity to play around with different real-time operating systems and understand what are the pros and cons and where can we make improvements and understand how to do things. And it's also open source. And probably my favorite quote from their whole thing is, it encourages the support and use of standard APIs. I was like, yes, our code's gonna work. Things are gonna be amazing. It has 18 processor architectures, 200 board support packages. So I'm like, okay, our stuff's probably gonna work in here. I'm not using anything weird, so it'll probably be fine. And it has a full-featured IPv4, IPv6, TCP/IP stack from FreeBSD. And that gives off really good vibes. Like, I'm like, Berkeley sockets, like, we got BSD, things are gonna work, and this will be amazing. And then add on to that it uses really modern compilers. And I was like, we are golden. Like, they have on their GitLab, they have a mirror of GCC, and it has like one of the most modern compilers mirrored in there. So I'm like, we are great. We can use my C++ 23 features and life will be great. And it also has a really active and amazing community. So for networking support, they actually ported part of the LibBSD kernel to RTEMS. And here's kind of the pictures of stuff from their website. It's kind of small, but you can kind of see they have all the different functions, the POSIX functions, and then they also have some really nice commands as well. Cool. So let's start with our initial POSIX example. So we're gonna call our init function post-initialization. So they do an init function that you can use to spawn off tasks, and in their typical example, you just in the init call hello world, and you verified that you can actually use RTEMS and get an output out of it. And I was like, okay, great, we're just gonna put our networking code. We don't need a client, we don't need a server. We have one file we're pulling, we'll just put it in there and it'll work. And with that, I got immediately network is unreachable error. And I was like, okay, this is rough. Don't know what's going on here. And there were kind of two potential errors, either an incorrect tap network configuration or incorrect RTEMS network setup. And I was running RTEMS on a simulated version of the hardware, so I probably didn't do something with like the tap interface to the bridge, trying to get internet across that. It was kind of what I was guessing the issue may be, but since I hadn't really used RTEMS before, I was like, maybe it's the init. So I ended up getting a lot of help from someone named Chris on their online community, and he was super helpful, and we got to here. And so actually one of the interesting things is I had to generate my own etc/rc config, and I was able to use DHCP, but I had to generate that and then bring it in for our initialization. Cool. And then looking at our configuration settings, this is a lot of initialization that needs to be done before we're actually able to use it, which is very different from our Linux operating systems, like what I typically use at work. So at work, I'm able to just kind of do stuff because stuff already exists. Versus here, I had to go make sure that all the right things were initialized. I had the right things set up in order to be able to do what I wanted to do. So part of my issues was most likely with QEMU. Who here has used QEMU before? Okay, that's like over half, like 2/3. So basically, it's a machine emulator and visualizer, and I was using a Xilinx Sync A9, and I had a tap connected to a bridge, and you can actually see the tap in here. It's QTAP, and it was pulling my hello.exe and running it, and I could tell it was running, but I was getting that error during runtime. And when I actually did ifconfig in my host machine, I was able to see that I was getting packets through the bridge, but I was getting nothing back. So I was like, okay, well, clearly I have something configured wrong. And so one of the really cool things is like, okay, we're now trying to debug. And when we are trying to test network issues in Linux, we tend to use a shell. We're like, we are not going to create a C++ program to test our network issues in our operating system. And that's great, but like I was like, okay, this is a different operating system. How do I do this? What do I do? And if you go back to the networking support slide, you notice that there's a ton of commands. And those are commands I recognize. I'm like, oh, we got ping, we got, what else do we have? We have route, we have ifconfig. I'm like, we're golden. We can see what's going on inside. And so we ran these calls, and you notice I'm getting the same host as unreachable when trying to get out. And I was also able to see, okay, I did configure stuff. I have some configurations that look on the surface reasonable. But in order to get stuff done for this talk, I was like, okay, I'm spending a ton of time trying to diagnose hardware issues and trying to diagnose my bridge not working. And so let's pivot and do something different. And so thank you to Robert for finding this XKCD meme. But like, I ended up looking at it and messaging with the RTEMS people, and they were like, well, we use FreeBSD. So like, why don't you just run it in FreeBSD? Everything's configured via file for your bridge, and you can test it that way. I was like, oh, this is great. Okay, fine. And I started doing that until I realized you had to install your package manager for you. And I was like, this is a can of worms that is going to take a lot of time. So I went down the can of worms a little bit, but it was kind of, we weren't getting much gain out of it. And in order to build everything, you actually have to build all your build tools, and that can take a really long time to pull. So I was having things run overnight for like 13 plus hours. I was like, this is taking too long to make progress. So if we look at what we got from our ifconfig, we do have loopback, and I set that one up correctly, and we can successfully ping localhost. And so I was like, okay, we're gonna pivot and we're gonna go look at doing like a client server on the same one and just using loopback, and that way we can verify that we are getting data going through and that we are able to use our Linux example and pull it over. And it's just gonna be a slightly different example. So we're gonna spawn 2 tasks, and RTEMS has both tasks and RTEMS threads, tasks and POSIX threads. And I use their default tasks to avoid more room for error and configuration issues, because they have some great examples on how to do it. And I just didn't want to have to deal with potentially missing configurations again, having to struggle with that. And we're gonna have the client socket connect to the server and receive data, and the server socket connect to the client and send data. So here's our client code. And this looks so much better. Looks really similar. There's one call that I don't typically see in Linux. Does anyone kind of see what it is? It's the exit call. So usually when I'm writing like a C++ program, I'm going to call return. Here, I've traditionally seen in the examples that I've seen that they called exit instead. So that was something that was a little bit different. And then now we have our loopback server code. Very similar, basically what you'd find on the internet trying to do a loopback. And now we're gonna look at our output. And we're like, yeah, we got our output. Things are working, we're able to connect. And that code, if we go back, looks pretty much exactly what we'd expect it to look on a Linux operating system using typical like C or C++. And so this is amazing. And things are working great, and that enables us to have that portability that we're looking for our code, and changing our returns to exits isn't the end of the world and something that can pretty easily be done. Cool. So here's kind of some of the things that I learned. Programming in Linux and Windows can be pretty hard sometimes. Like I can fall into a lot of pitfalls when it comes to networking, but when you start getting into an RTOS and doing stuff with like additional layers of abstraction and visualization, you can end up having additional issues that you don't expect to have. And everything needs to be configured and initialized unlike our typical OS. We aren't having to call all this init stuff in order to verify things are going to initialize and be able to even use our threads. But that's actually really powerful as well because we have control of what we use. So if you aren't doing something like our use case where we're actually running Borderline a web server up in space, you don't need all the capabilities that we're using and you can save the space. So now we're gonna look a little bit at Boost.Asio because I don't just wanna run raw sockets. I want to use a library to run sockets. And we already wrap Boost.Asio at work, so I was like, this is great, everything's gonna be good. So I looked at the supported platforms and I was optimistic. I was like, okay, things are great. We got GCC and you can tell, so the GCC version that we're running with RTEMS is 13.4. I think it's like one minor version lower than my current version on the Linux system I was running. So like, this is amazing, this is awesome. And then we are running on something that's kind of FreeBSD, Linuxy. There's hope, maybe this will all work together. Now for Asio, I was like, okay, we gotta pull from source because we don't know what's going on, what we need for precompiled headers, and it's header only, so we should be okay. And I was missing some of the pound defines that were needed, so I was able to redefine them, and then I was able to start running. And I was actually able to successfully run IO context, but anything post IO context, I ended up running into host not found. And so there's definitely some interesting stuff kind of going on in the background there. And I haven't started tracing that down, but that's something I want to keep doing in the future to understand kind of what's weird here, what's going on, what do we need to do. But we were able to pull in the library and do the pound include and pound include Boost.Asio.hpp and get it in. So there's a lot of hope for bringing Boost in and using it with RTEMS. So now we're going to jump a little bit and look at how different libraries figure out what operating system we are. Because that seems to be our problem when trying to pull these libraries in, is things are wrapped with like, if not defined Windows, then we're gonna do this, or if defined Linux, we do this. So first we can look at what the system name is, as well as the machine. And then we start looking at all these random pound defines that you can just randomly find in random libraries and try and figure out which ones are used where and which ones are valid. And so I just wrapped them and sent a C out, and I was like, we will figure out which one this is. And so, cool. Does anyone have any guesses as to which ones we got out on this? It's kind of wrapping FreeBSD, but it's also kind of not. Does anyone think any of the __ whatever BSD ones output anything? Okay, got no shakes. Cool. So we got RTEMS. We got it's running on ARM, which are both true. That's what we're emulating. And POSIX version is defined. But none of the BSD preprocessor outputs are defined. And this is really cool because if we use this POSIX version, we could have that compatibility across all of these different libraries because most things wrap something that's POSIX. But if you start looking at it, a lot of things just go straight to, is it Linux or not? And so we're losing that ability for these different libraries and these different use cases to be able to interrupt and have that portability that we need. And so that's probably what's going on underneath the covers in Boost.Asio, is that some things are using, is it Linux, in order to go down. So now we're gonna look a little bit at ZeroMQ. Who here has used ZeroMQ before? Okay, we got like half-ish. Okay, so it's a open source universal messaging library. I like to think it kind of does fancy sockets. So they do like pub sub, push pull, client server, but it's a little bit custom, and when I tend to use it, I tend to want to use it on both sides. I mean, it has support for a variety of different transports as well. So when we look at our ZeroMQ libraries, we have a bunch of libraries here. So I pulled all the C++ and I think the C ones too. And I was like, okay, which one are we gonna choose here? Because there's a lot here. And I'm like, I don't know which one to pick. So first, we're gonna start knocking some of them out. The ones that wrap something else, I'm like, if the something else doesn't compile and work, this isn't gonna work either. And so that left us with Libzmq and AZMQ. AZMQ is wrapping Boost.Asio. And so since we need to figure out what's going on with Boost.Asio, that's probably gonna work once Boost.Asio works. And then Libzmq, it's actually C++ 98 with some, or I think, yeah, with some C++ 11 fragments. I think it may actually be C 98, but yeah. So that's the one we're gonna look at. So now I started digging kind of under the hood. I feel like the best way to understand what's going on with the library is not be afraid to start diving backwards into the source code. And so I was like, maybe we have a hope of things working. And I looked at ip.cpp because I was like, we got this open socket call. Things are gonna go great. I can see the socket. And I was like, there's no Linux pound defines in sight. Maybe there's hope. And it's only looking for if it's not Windows. So we aren't Windows, maybe things will work, maybe things will be fine. This looks really great. But with that, because we're running on different hardware, we had to manually build from source. And RTEMS, as example, uses WAF, and you can potentially use CMake, but I was just kind of using the example to go off of. And WAF isn't one of the pre-configured build options for Libzmq. And so since it's not a pre-configured build option, it didn't have the specific pound defines set in its build process. And so I was trying to pull them from a different build process, and it was detecting that I wasn't actually who I said I was when I was trying to use it. So yeah, it was not very happy at me for trying to jump around the problem. But there is the potential still to pull in the package. So maybe since it's a custom GCC version, I can still use a package manager to pull it in, or switch over to doing something in CMake and then pull it in that way. And it can potentially also work if all of them are accessed via not Windows. It looks like things will work. So I think there's a high potential that we can get things to work without having to change a ton of code. Cool. So some of the future RTEMS investigations to do. So I struggled a lot with getting a hardware set up and trying to run things, which I think is a really common issue with doing embedded work, is the minute you think things will work really quickly, nothing works as fast as you think it will, and things don't tend to work. And then you get stuck in really long compile times. And so you just burn a ton of hours doing not a lot of things. So I think investigating some of the other POSIX implementations, such as pthreads, could be really valuable. That way our threading libraries could be able to work across, as well as being able to do things such as using stood thread to do things. I really want to try running our flight software in RTEMS, but we need to figure out those kind of big blocks, such as Boost.Asio, and we have a bunch of other little libraries, so figuring out which one of those we can get over. And then using the variety of Boost libraries in RTEMS. RTEMS does have a variety of different packages, such as LibBSD, so I think being able to add additional packages such as Boost will enable this community to start using C++ more and use some of the modern tools that we love to use when we do application code, when we do code with Linux, and that'll make it a lot more accessible for different people who aren't in the embedded space to get into the embedded space and try doing different things. And then additionally, create a minimal RTEMS example for different POSIX implementations. One of the hard things about RTEMS is there isn't a ton of examples, and a lot of the things I was using for help were the test code. And so it was look at the test, this has the implementation. And that works really well when you don't know exactly what's going on, until you are kind of confused about what you should be including and what you shouldn't be. And we can definitely, I think some minimal examples would make it a lot easier to access and a lot easier to use. So I really just wanted to say a thank you to the RTEMS community. They were super helpful. I did a lot of late nights trying to get help from them, configuring and initializing the networking, and for helping me figure out this whole ideal. And then the amazing C++ community has been helping me with my random questions that I've had on this, and that's been really helpful as well. So let's make our libraries work for everyone. I think one of the things we need to make sure to do is make our OS APIs match one of the standards. We need things to be able to use what we think they will use and be able to have that portability across different things. And then for the libraries, I think we need to start embracing our non-Windows Linux operating systems in our design. Getting some of these CI pipelines to also be running different operating systems that aren't the normal ones. So that way they're actually considered in these design things. And that's something when you look at these future things, such as some of the networking things being added to the standard library, it's we need to consider our whole user group when it comes to this, or things aren't going to work how we want them to, and we're just going to be left with a bunch of features that aren't actually operational. And then from the user side, I think one of the things to learn is you never know when you need to switch operating systems. This is something we've been seeing a lot at work of We've done some stuff in Linux, we've done some stuff in Windows, and we've had our Windows machines wiped a couple of times, and so we have to keep reinstalling WSL. And so figuring out like what operating systems you need and how to quickly get set up on it, as well as being used to using a variety of operating systems, is really helpful. And then use your libraries, but also don't be afraid to build wrappers around the libraries that you use. So if you wrap your library, then you don't have to interact directly with whatever APIs could change or have issues. And then don't be afraid to ask the operating system experts for help. They love to help and they're super helpful. And they were probably the most impactful in me being able to get things working. And then check that you're using the standard. So big thing, if you're using the standard, that'll allow you to have that capability to be portable across a variety of different things. So we want to make sure that we have that capability moving forward. So yeah, that's kind of some of the things that I learned trying to investigate this. Thank you. Are there any questions?
Thank you for the great talk. I really enjoyed it. We experienced loads of similar things related to POSIX. We ship software on TVs, so it's not quite satellites, but also similar area. Basically I had a question. Do you guys ship your updated binaries directly to satellites, native executables? That's the one. And second, what in general the constraints that you get there that force you to use those operation systems? Basically the choices that you made, basically what are the constraints there?
Yeah. So for the second one, a lot of our constraints ended up being for our initial satellites were ease of use. So we're running Debian right now, Debian wrapped in Docker, so it's able to restart. So we're using some really modern, really interesting architectural decisions to enable that to happen. But when it came to this smaller architecture, it was a lot of pre-design that was happening before many of us were there and being able to make those design decisions. And so they just kind of went with, when you look at that document, those streets, and you're like, what makes sense and what makes sense for space? And space is a really weird world because you like things that worked before. And so when we try to do that, it's they kind of went with those decisions. And then because space is a lot of long lead, things had just started to come in, and so there wasn't the ability to pivot and change.
Fair enough, yep.
And then for the first one, we tend to try and send our code up. I think Julian, how do we get code up? Yeah, we directly send it up via basically file sharing, send it up.
Okay, cool. Yeah, thank you. Yeah.
Hey, did you try any other of the RTOSs that you had on the screen up there, like Zephyr or something? And how was the support for those? Because I think the two that you mentioned are quite old, or at least started earlier.
Yeah. So I just worked with RTEMS and FreeRTOS. I've heard of Zephyr and touched it a little bit, but I didn't choose to deal with it this time. I think that's something that would be really worth exploring in the future.
Yeah, I know your talk is about POSIX, but I couldn't help notice on the slide with the capabilities of RTEMS being built on top of BSD that it supports a lot of things that are BSD but not POSIX. For example, it claims to support KQ. What are your thoughts on, because when you showed all of the macros, RTEMS wasn't identifying as free BSD. What thoughts do you have on, as you proceed to work on integrating with ASIO, for example, trying to make it figure out that the operating system is like BSD and use those things that are non-standard, kind of flipping the script on your talk?
I think that could be really smart. I think for a lot of the use case that we're looking at doing, we're using already Linux. And so I kind of like that idea of going down to the most common thing that we can use across these different things. So that way we can have that portability across our software. But in general, I think for things like ASIO, it makes a lot of sense since the library already has those capabilities to take advantage of using the tools that are already available and the flags that are already available. So I think that could be the best option for that.
Given that you've identified some compatibility, portability issues in these libraries, what sort of upstreaming might you do, or are you allowed to do?
Yeah. So I'm really lucky here, and I think that's something that I've seen struggle with a lot in some of the stuff we've been doing is we rev so fast that trying to push stuff upstream becomes really difficult. So a lot of our stuff we just end up forking or people have local copies of and just keep modifying there. Since this is more of a personal thing that I've ended up messing with and we aren't currently using it at work, I actually was already able to. And one of the things, there was an extern C that was missing. So I included a header and got a ton of like missing function calls. And so I was actually able to put that as an issue. And I think given how much Boost is important to C++ and this community is important to C++, I'd really love to spend some time trying to figure out how to get Boost into there and figuring out kind of the upstream side of that.
Cool. Thank you.
Yeah.
One of my worries when working with real-time operating systems is pulling in a library that might compile just fine for that operating system, but it might use some system calls that violate real-time constraints. Have you ever had any experiences like that, or experiences with real-time operating systems and third-party libraries that didn't have real-time support, and what kind of problems would you have with those?
So a lot of the issues I've had, we mostly do stuff using Linux, and I've done a little bit with like real-time extensions in Linux, so I don't tend to have as many of those issues. But I think in general, trying to figure out having someone on the team that does the embedded systems with the real-time operating systems and kind of knows what's going on with it. So that way it isn't just up to the developers, but it's also like who are using the library, but it's also the library authors care about it and have an investment in the community is what's going to make it successful and think about these things. Because all of us come with a different mindset and a different idea of what's important and what's not. And so if we come into it with those different ideas, we'll create the best outcome because we don't have a bunch of people thinking the same way.
Thank you.
Yeah. Cool. Awesome. Thank you so much, everyone.